We've talked about using transformations when the conditions for inference are violated, but another reason that we might want to use transformations is to standardize the slope coefficients. So let's say that we're looking at predicting acceleration times for cars, and we want to know which explanatory variable, weight or horsepower, has the largest impact on the acceleration times. So we could think about comparing the slopes, but it's actually difficult to compare because remember that units are important when you're talking about the slope. And it's really hard to compare a 1 pound increase in weight to a 1 unit increase in horsepower, whatever that is. So one option to make these units comparable would be to standardize the variable. So that means that we're going to subtract the mean and divide by the standard deviation. So I've just got a little snip of the data set here. I've got acceleration times in seconds, horsepower, and then also the standardized version of that variable, weight, and then the standardized version of that variable. So I'm just going to kind of pick one and describe what's going on here. So this is the standardized weight of negative 0.713. So we see that it's negative, and that means that it's below the mean, right? Because the value minus the mean comes out to be negative. So this would be telling us that this car has a weight that is below the mean, but we want to be more specific than that. We want to know how far below the mean it is. So besides just positive and negative, we're putting this in terms of standard deviations. So this is telling us how many standard deviations above or below the mean we are. So this car has a weight that is 0.713 standard deviations, that's our unit, below the mean weight. So if you think about like z-scores from your intro stat class, that's basically what we're doing here. We're calculating z-scores for every single value in our data set and then using that as the explanatory variable instead of the regular unstandardized horsepower or weight. So let's do this in JUMP. So I'm going to do analyze fit y by x, and I'm going to try to predict acceleration. And for now, I'm just going to do weight. So I'm going to right-click weight. And instead of clicking transform, I'm going to go down here where it says distributional, and I'm going to do standardize. And now I have the option to use the standardized weight as my explanatory variable instead of the regular weight variable. So I'm going to click OK. And I notice that the axis has changed. I've got standardized weight here on the x-axis, and I've got positive and negative values. And then I'll just fit the line as usual. And we'll be interpreting the values in this parameter estimates table. So I want to give you a second to think about this. So now that we're using a standardized version of weight as our explanatory variable, how is that going to change our interpretations of the intercept and the slope? So I've got them started here. I want you to think about how to finish those interpretations. I also want to make some comparisons. So compare the output up here, which is the standardized version of weight, to the unstandardized. What's the same and what's different? Also compare the model that uses the standardized version of weight to the model that uses the standardized version of horsepower, and see if you can decide which one has a bigger impact on the acceleration times. So go ahead, pause the video here, and see if you can answer these 4 questions. So let's start with the interpretation of the intercept. So usually the intercept would just be the predicted value of y when your x variable is equal to 0. But let's think about what it means for the standardized weight to be equal to 0, right? It's not that the car weighs 0 pounds, it's that there's no difference between the weight and the mean weight, right? So this is another way of saying that we're predicting the acceleration time for a car with the average weight. So this is in some ways an advantage over using regular variables because a lot of times the intercept is not meaningful. Like in this case, a weight of 0 pounds for a car doesn't make any sense, but usually the average value of the explanatory variable will be meaningful. So it kind of makes sense to have the predicted value for that weight. What about the slope? So the slope would normally be the change in the predicted value of y, or a 1 unit increase in x. So the question here is really, what is our unit, right? Our original units were pounds, but we basically converted that to standard deviations, right? If we look at the standardized version, we've started thinking about how many standard deviations above or below the mean are you, and that becomes our new unit. So the acceleration times are predicted to decrease by 1.15 seconds, that's the slope, as weight increases not by 1 pound, but by 1 standard deviation. So let's compare to the output using the unstandardized version of weight. So the values for the intercept and the slope and also their standard errors have changed here. These are different than they were before. And that's not surprising because we just said that they have different interpretations. So of course the numbers are going to be different. By the way, notice that the unstandardized slope is extremely small. It looks like a really small value. That's because 1 pound in terms of weight just really isn't a meaningful increase. So maybe it makes more sense to think about it in terms of standard deviations versus using such a small increment as pounds. But if we look at the t-test, the t-statistic and the p-value, those are actually the same as before. So it doesn't matter whether you use the standardized version of X or the unstandardized version of X. It turns out that both of them give you the same evidence of an association. So that kind of makes sense. We wouldn't think that just transforming the variable, putting it on a different scale, would suddenly give us stronger evidence of an association between these two things. So that kind of makes sense. And actually, if we do a side-by-side comparison, we'll notice that there's a lot of things in common between the regular regression and the standardized version. The R-squared is exactly the same, the root mean square error is exactly the same, and just looking at the picture, they look exactly the same, except that the scale has changed. So it turns out that both of these models will give you the same predicted values. Obviously, the calculations look a little bit different, but the outcome is the same. So even though it's not shown in the output here, I'm also just going to put a note, also the same strength of association. So that's like our R-squared or our root mean square error, and even the same predicted values. So that doesn't change depending on whether it's standardized or not. And the last one, coming back to sort of our original goal with these standardized slopes, is to compare to the standardized version of horsepower. So looking at the standardized slope here, we can see that it's further from zero, right? This is a larger slope, at least in absolute value. And that's really what we want to compare. We're thinking about the steepness of the slope, not really whether it's positive or negative. So it's larger in absolute value than the one for weight, which was negative 1.15. So that's telling us that horsepower is the one with the bigger impact. Horsepower has a bigger impact on the predicted acceleration. And we still want to keep in mind that this isn't necessarily a causal relationship. It's not necessarily cause and effect because this is an observational study. So there could be confounders. We've actually talked about those in the past. But just in terms of the change in predicted values, horsepower has a bigger impact.